this was our definition of differentiable function at a point. Now, if I want to analyze this more exactly, what I have to do is take the derivative as a function itself. So it's like takes the point P in the domain and maps it to the linear transformation. So I have to take the set of all linear transformations from V to W, because this is a linear transformation for V to W, whose which I can easily compute by this theorem now. I will just take the partial derivative in the direction V, which uh, let's just say that is easy to compute, um, because I have not a approximating function, just a exact um, take the difference, take the limit, which is actually computable, I guess. Now, if I want to analyze this set more closely, uh, I would have to analyze this set more closely. I mean, what um, I can write this set in a very proper way, easier to handle sort of way. Set of a linear transformation from V to W should be made into a nice space, a normed vector space to be exact. So what will I have to do is take the set of all linear transformation from V to W, where V and W are vector spaces, and define two operations on T1 and T2 belonging here, where it will define a new element. This will define a new element in the same vectors, same set in this way, T1 of x plus T2 of x, where this addition is happening in W, because the T1 of x is an element of W and T2 of x is an element of W. And similarly, I can define a scalar multiplication, and this way of defining something is called pointwise, because I'm defining it pointwise for all x. For all x has to be in V. So now this L of V to W becomes a vector space. And this is true for any two vector spaces over the same field, but let's just say the field is always real. Now I will also have to put a norm on it to do double derivative, for example. So I want to define something like a norm for T, where I have to refer the book. So the norm of T has to be, so here I have to define a operator norm on this set, which I would define as mm, which is same as this norm. So the definition they have used is, we will use something of okay, so they have defined something called a bounded linear transformation, where there is a alpha greater than 0, such that alpha, like every vector has a limit, every ball where mod x is something fixed constant, that ball will be mapped to some something of radius alpha times mod x. So, and they have used the smallest of that alpha to define the operator norm, like the norm of the element of linear transformation from E to F. Now that is also equivalent to just taking supremum of AX, the norm of AX, or the supremum of AX divided by X, the norm of that, where X is not equal to 0. Or so okay, so the norm A mod x where x belongs to the norm A. So you have to do something of this form where norm of t is defined as supremum of t norm of x. This is a this is the norm of w because t of x is an element of w such that norm of x is equal to 1. So I'm taking the ball in V and checking wherever it is getting mapped to in W and taking the supremum of whatever norm there, whatever norm is the supremum, supremum of the norm, the maximum or the least upper bound exactly of the all the norms t of x, all the norms of t of x's, where I'm taking all the x's from the open, from the ball, the surface of the ball actually, mod of x is equal to 1. Um, I would think that this is correct. This is called the operator norm. It has equivalent notions, and so now, and we can also check that all works out with the additions, scalar multiplication are all proper. We can, and using this norm, we have made linear transforms from V to W normed normed vector space. So using that, I can now define continuity of this guy. So if dpf of dpf exists as all point, then dpf is a actual function, and if dpf is continuous, and continuous is doable because I have a norm in this set, norm in the domain, and there are these two are two metric spaces now. So if this is continuous using the epsilon letter definition, then we say f belongs to continuously differentiable function from u to w. And now we want to define the double derivative. If I want to define the double derivative, then I would encounter a problem of simply problem of this is from u to w, and the derivative function would be u to l v to w. Then if I do this operation twice, I would have to do this is another norm. This is another norm vector space. I will take something like a double dash and just do this operation twice. So the set that will be is the domain is the same thing, but now I have to understand this set. This set is a pretty weird set. We just defined what uh, vector space is. Now we just define this operation twice. So what this will do, a typical element of here, what it will do is it will take some v1 from v and will map it to some linear transformation t of v1. So what it would essentially do is take another v2 element over here and it would map it to some element of w. So what I'm essentially with the t, what the t is doing is it is taking two elements of this form and it is mapping to something like w. So this space seems to be same as the set of all bilinear function from v to v cross v to w. This is the notation, and this is actually if I also define the norms in this space in the same way as we have defined in the previous one, that's the supremum of all the it's slightly different, it's in the book. then there would be a continuous isomorphism. So they are topologically isomorphic. That is the terminology that the book uses. So now we can use that definition to define what is a T2 of F. What tensor product does is just makes this a whole lot of simpler. The simple thing that they do is to understand that we have to consider this isomorphism that L V to W is isomorphic to the dual of V tensor product with W. What is the dual of V? It is a set of all linear transformations that V take V to R. So the dimension of this guy would be the same as dimension of V. There would be isomorphisms between them, but they would not be canonical. So they would be not a natural transformation. Uh, natural coming from the definitions, it would depend on the basis. That is the new version of the not a canonical isomorphism between them. The meaning of that. So what V star element of V star does? Element of V star is takes some vector V and element of V star I would write as some V2, let's say, and V1. It would take some element and it will map it to some real number. And how do I understand this isomorphism? This is a linear transformation. A linear transformation can be written in terms of a basis. What it would do is take the basis of TIs and it would map it to some T of VIs and it would be something like that. A typical element here would look something like Vi star tensor product Wj, where Vi star is the basis of V star and V sort of all Vi stars are the basis of V star and Wj sort of all Wj is the basis of W. And which linear transformation would this represent? The linear transformation that it would represent is Wj Vi would represent was Vi of X Wj. That would be a Ij. It would take some element X from V. This would be element of V. This would be a linear transformation because these are linear transformations and this would be just a real number because this is just real number and I'm scaling the Wj with that real number and I'm adding them up. So if the element of this form, a typical element here is mapping on a typical element here and I can also show that this doesn't depend on any basis, I think. So yeah, this is a pretty much a canonical isomorphism. If I use that, then what my derivative function becomes is a lot simpler. This just becomes a function from that, and I am also inducing the norm from this one to that one. They have the same function, and this would just be a bilinear function, and bilinear function would look something like this. What we would have done is do attach the V star with this one, but because the tensor product operation is also associative, because there is a canonical isomorphism between them, they, we can just remove the brackets and write it as this. I'll just keep the brackets removed. So this would what would be a double derivative. This would be a bilinear function at a point. I would define that to be the d square of f, and d square of f equal to fixed at a point would be a bilinear function. And there is another theorem which says that d2 of f will take two different elements of v. It would take it in such a way that v2 of v1 will map it to same element as v1 v2. This is called symmetric. The linear transformations, bilinear transformations that they do this are called symmetric bilinear transformations. So we are not just working in this set, we are working in a smaller set which is only concerned with symmetric transformations.